What specific problem does STORM aim to solve in the context of video-based multimodal large language models, and what challenges does it address regarding temporal encoding?
STORM aims to solve the problem of inefficient processing and understanding of long videos in video-based multimodal large language models, video LLMs, by introducing a novel temporal encoder that integrates temporal dynamics earlier in the processing pipeline. The primary challenge it addresses is the lack of explicit temporal encoding in existing models, which forces the LLM to infer temporal relationships solely from static image sequences, leading to significant computational burdens and information loss due to naive frame subsampling. By employing the Mamba state space model as the core of its temporal layer, STORM effectively compresses historical information and captures comprehensive spatiotemporal dynamics, allowing for a more efficient representation of video content. This approach not only reduces the number of visual tokens processed by the LLM, but also enhances its ability to generalize to longer temporal contexts, ultimately improving both performance and computational efficiency. Thus, STORM significantly mitigates the limitations of traditional video LLMs in handling long video sequences.
How does the STORM algorithm work? Illustrate its methodology step by step, detailing how the Mamba temporal encoder integrates with the vision encoder and LLM.
The STORM algorithm operates through a structured methodology that enhances long video understanding by integrating a Mamba-based temporal encoder with a vision encoder and a large language model, LLM. First, the algorithm processes video frames using a vision encoder, specifically SIG-LIP, to generate initial image tokens. These tokens are then downsampled to reduce their dimensionality before being fed into the Mamba temporal encoder. The Mamba encoder performs a bidirectional spatiotemporal scan, capturing both spatial and temporal dependencies across frames, which allows it to compress historical information into enriched visual tokens that summarize the temporal dynamics of the video. Finally, these enriched tokens are passed to the LLM, where they facilitate improved temporal reasoning and enable efficient token compression through techniques like temporal and spatial pooling, ultimately enhancing the model's performance while reducing computational overhead.
Can you provide a simple illustrative example of how STORM processes a video, detailing the interaction between the temporal projector and subsequent token compression methods?
STORM processes a video by first utilizing the Mamba-based temporal projector, which integrates temporal dynamics into visual tokens derived from each frame. For instance, when a video is input, the projector performs a spatiotemporal scan across the frames, enriching the visual tokens with information from both the current and previous frames. After this temporal encoding, the enriched tokens undergo token compression methods, such as temporal average pooling, which averages the visual tokens from consecutive frames to reduce redundancy. This results in a smaller set of tokens that still encapsulate essential temporal information, allowing for efficient processing by the LLM. Finally, at test time, a training-free temporal token sampling can be applied to further reduce the number of tokens fed into the LLM, enhancing computational efficiency while maintaining performance.
What are the key theoretical or practical benefits of using the STORM method compared to existing video processing strategies? In what ways does it improve efficiency or performance?
The STORM method introduces a novel temporal encoder that effectively integrates temporal dynamics into visual tokens, addressing the limitations of existing video processing strategies that treat frames independently. This integration allows STORM to compress historical information across video sequences, significantly reducing the number of tokens processed by the LLM while preserving essential temporal information. Practically, STORM enhances computational efficiency by enabling the processing of long videos without the need for extensive system optimizations, allowing it to operate effectively on a single GPU. Empirical results demonstrate that STORM achieves state-of-the-art performance on long video understanding benchmarks, outperforming existing models like LongVU and LongVILA, while also reducing inference latency by up to 65% through test-time temporal token sampling. Overall, Storm not only improves model performance but also maintains high-level understanding with a drastically reduced computational load, making it a significant advancement in video-based multimodal LLMs.
How was Storm validated in the experiments, including the datasets used, benchmarks for performance, and metrics for evaluating its effectiveness?
Storm was validated through extensive empirical evaluation across multiple long video understanding benchmarks, specifically EGO-Schema, MVBench, MLVU, Long Video Bench, and Video MME. The experiments compared Storm against a variety of existing video language models, including those designed for long context inputs, to assess its performance. The evaluation metrics included accuracy rates, with Storm achieving state-of-the-art performance, such as 71.3% on MVBench and 72.5% on MLVU. Additionally, the experiments involved analyzing the impact of different token compression strategies, such as temporal and spatial pooling and test-time temporal token sampling, on both performance and inference latency. The results demonstrated that Storm not only maintained competitive accuracy, but also significantly reduced computational overhead, showcasing its effectiveness in long video processing.
What specific results were observed with Storm in comparison to existing methods, and what implications do these results have for future video understanding technology?
Storm demonstrated state-of-the-art performance across all long video understanding benchmarks, achieving 71.3% accuracy on MVBench, 72.5% on MLVU, 59.5% on Long Video Bench, and 63.4% on Video MME, outperforming all open-source video LLMs, including those specifically designed for long context inputs like Long VU and Long VLA. Additionally, Storm's efficiency was highlighted by compressing visual tokens to 25% of their original number while maintaining competitive performance, and further reducing the token count to just 12.5% through test-time temporal sampling, which improved results on certain benchmarks. These results imply that Storm's innovative integration of temporal dynamics and token compression not only enhances model performance, but also significantly reduces computational costs, paving the way for more efficient and scalable video understanding technologies in the future. The ability to process longer video sequences effectively suggests that future models can leverage similar architectures to handle increasingly complex video data without sacrificing performance. Overall, Storm's advancements indicate a promising direction for developing more capable and efficient video language models.